Time for me to confess in video. I did not finish marking the test, but you'll have them on Thursday, I promise. I promise. Okay. Sorry, let me just. Good.
Oh, okay.
Okay. Today we're starting sort of the last chapter, which is very exciting. I say sort of because we're just going to dip our toes into 9.1, but you won't even feel it, I promise. And so I like ending on this chapter because we're not really going to do any more inference. We can, and we will kind of touch on it a little bit. So no confidence intervals or hypothesis testing. We could, but we don't, right? And so we keep it nice and breezy here in the last section. So I like to end on a high note. And so what is regression? Regression is a line of best fit. So we're just going to spend some time talking about how do we make a line of best fit. In fact, we're only going to focus on linear regression, which is a straight line, right? And so a straight line okay. You might think back, or if I say y equals mx plus b, I say y equals mx plus b, you say, yeah. Right, a straight line, maybe it doesn't ring a bell as a straight line, but it is the equation of a straight line, right, where we've got some slope m and some y-intercept b. You could use ax plus b or b plus ax or whatever weird thing you want, but m is the slope and b is the intercept. Technically the y-intercept, but I just call it the intercept because we rarely care about the x-intercept. Right? So we're going to be making straight lines. Ah, neat. Why? Well, let's have a look and see. If we have a straight line, it's kind of implied that we have some sort of scatter plot, right? We have some relationship between a value x and a value y, right? Otherwise, it's hard to fit a straight line, right? And so what if we have, something that looks like this? I remember in, I don't know, chemistry 11 or 12 or something, where we had made a scatter plot like this, which we absolutely could do by hand. And then we were just told to fit a line of best fit. And we just took our rulers and went like this. Oh, yeah, that looks so good. There's a little bit more to it than that, right? But intuitively, what are you doing? You're trying to minimize the distance between the points on the line. And so that's what our mathematical formulas will do. And so it's not that out of left field or anything, but we have mathematical formulas that will do this. Okay. Digging deep to the beginning of the term, way back in the beginning, we said that, okay, we're going to have a response variable, and that's going to be on our y-axis, or if you want, you can call it a dependent variable, but I call it the response variable. And then we're going to have an explanatory variable on the x-axis. I like to use explanatory because it has the x in the word, and that kind of guides me to which axis to put it on. Or if you want, you can call it the independent variable. Okay. So our goal here, right? If chapter 8 is just about fitting lines to some scatter plot, there's got to be some goal here. What are we trying to do? Well, we're trying to say, okay, what if I have some value of x? Then my goal is to predict what the response would be. Of course, the thing I'm interested in is the response variable. So maybe it's easy to collect information on x, but difficult to collect information on the response. So then what we do is we take that value of x and we plug it into our line of best fit to predict the value of y. Okay. And so regression, because in this course we only talk about linear regression, in fact, it would take maybe another or 2 stats courses before you got into nonlinear regression. So that's why all regression for us is linear. So I just call it regression. Okay. So regression is when we are given a value of x, right? And we use it to predict the value of y. When we are given a value of x and use it to predict y, right? Where y is the response variable. That's what we're building up to. And once you get the hang of it, it's quite fun and easy in comparison to what we have been doing, right? And so ending on a high note here, home stretch. All right. Anything else I wanted to say here before we get started? No, I don't think so. So we're just going to establish some facts, some terminology, and then eventually we'll start building this line. So for us, most often we're going to have, let's go back to this fake example here. We're going to have a numerical variable on the x-axis as well as a numerical variable on the y-axis. It is possible to have a categorical variable on the x-axis as an explanatory variable, but we're going to focus on numerical variables, and then I kind of sprinkle it in at the end. Well, what if it's categorical? We can do that. The main thing is that the response variable has to be numerical. Otherwise, we use different methods that we do not teach in this course because it's not very common. Okay, so for us, the y variable has to be numerical. So y must be a numerical variable. Your x can be one or the other. We're going to focus here on the numerical. We're going to introduce it by way of example. And so if we think about, let me just use this space here, the previous slide still. The response variable is the thing that we want to predict, right? And so the response variable y is the variable we want to predict. Is the variable we want to predict, right? Or just generally the variable of interest, or the variable of interest. Sometimes it's obvious which one is the response variable and which one is the explanatory variable. In the following example, we could have just as well swapped them, and that happens quite a bit. But in that case, I would just give you the scatter plot, and then it's your job to know that the one on the y-axis is the response and the one on the x-axis is the explanatory variable. Have I given you that cute example of how to remember which one's the x and which one's the y-axis? I had a student tell me one time, she's like, oh, I can't remember them at all. So then she imagined that the y-axis was falling on some little guy down here. And he's like, no. And that's the x-axis. So that's cute. If you can't remember which one's which, all right, the x is on the bottom. Which we need to know, so whatever works, right? But when she told me that, wow, that is very elaborate and very cute to think about. Okay. So the thing that we're interested in is going to go on the y-axis. In this case, we're going to talk about the poverty rate versus the high school graduate rate in all 50 US states and DC, which is not a state, very particular, I guess. And the percent of residents who live below the poverty line, which is defined as any income below $23,050 for a family of 4 in 2012, which is outdated, obviously, but those are the parameters. So, as a warm up, right? If I gave you this scatter plot, then I would ask you, what is the response variable? What is the explanatory variable? So if you just have this scatter plot, of course, I would have the labels on here. So from the scatter plot, the response variable, well, it's the one on the y-axis here, right? So it's going to be the percentage in poverty, right, in each state. Yeah. What's the explanatory variable? Well, here from the scatter plot, it's the percentage of high school grads, right? Each state has some percentage in poverty and some percentage of high school grads, right? And so each point represents a state or DC, whatever. Let's just generalize as a state, okay? And so, right, we've got these ordered pairs all in our scatter plot representing each of the states. Okay? Now, when we're given a scatter plot or when we've made a scatter plot, one of the main things that we want to do to start is just to describe the relationship. Okay, and I guess I'll use this next slide, or I'll just make a page. Make a page. No lines. Oh, dang. Okay. Remember when we were making histograms and I said, okay, you have to be able to describe the distribution, and we talked about the shape, the center, and the spread, right? And the shape, whether it was normal or non-normal, determined which was the appropriate measure of center and spread, right? We're going to do a similar thing here with scatter plots. And so given a scatter plot, we need to describe the relationship. Describe the relationship between just generically X and Y. If you wanted to, you could be proper and say between the explanatory variable and the response variable, but shorthand X and Y. So the first thing that you're going to need to talk about is whether it's linear or non-linear. Linear versus non-linear. We did that before, right, with the normal or non-normal, right? We talked about a couple of special cases, skewed to the left, skewed to the right, bimodal, but in general, we just summarized it as, is it normal or not, right? So we're going to do the same thing here because all our methods apply to a linear relationship. So we better hope that it looks linear, right? You don't want to have something that looks, you know, like this, and you're trying to fit a straight line to it to model that behavior. That's a terrible model, right? And that's really what we're doing, is we're modeling this behavior, right? And so, but if you have something that looks like this, it's reasonable to model it with a straight line. So that's step number one. Okay. And we're not going to talk about nonlinear relationships because they can look all kinds of ways. Okay. They need to tell me that it's linear. It will be. Don't tell me it's nonlinear, then we can't do anything, right? That'd be bad. The second thing we need to talk about is the strength of this relationship. Is it strong? Is it weak? I only use those two classifications, and you can kind of get jiggy with it as you go. Moderately strong, moderately weak, kind of trust your gut. But for the strength, I'm going to go for strong versus weak. If you see a pattern, I would call it strong, or if the pattern's not very strong, then you could say moderately strong or something like that. But just as a guide, if you can kind of squint and see something, right, then it's strong enough for us. So if you see a pattern, the relationship is strong. Is strong, or can get weird with it, moderately strong. If you don't feel comfortable saying strong, that's fine. But for me, I just want that classification of a strong or a weak relationship. So if you don't see a pattern, what would that look like? You've got your y and your x. Well, no pattern at all. It's just this cloud here. Right? The problem with this, and why we wouldn't fit a straight line to this, is because I could fit a straight line like this, or like this, or like this, or I don't know, get crazy like this, right? There's no anchor. And so a weak relationship we don't model, because any one of those would work, but none of them would do a good job, right? You can plug in some value of x. Ultimately, what you would land on is just straight across like this. While you can plug in this small value of x and get this predicted value of y. You could plug in a large value of x and get the same predicted value of y. And so that model doesn't do anything. And that's the problem. We don't model weak relationships. So for us, you really only have one option. It's going to be linear, and it's going to be strong, or some version of strong. Then the direction of the relationship. The direction is either positive or negative. So a positive relationship is going to be increasing together. And just to emphasize, I put a little arrow on there, mostly to show that it's moving up in the positive direction, right? And so obviously there shouldn't be an arrow there, but I find that it's helpful, because then, I'm just going to copy this. If I have a negative relationship, it's going to be going down like this. Depending on the relationship, right, one of these will apply and there's nothing in between. So it's either positive or it's negative. Okay. So if I asked you to describe this relationship, which is something that I make you do on the final exam, I make you tell me what the response variable is. I make you tell me what the explanatory variable is. Hey, this is already 2 marks on the final exam. I make you describe the relationship, right? And so look at us, we're just raking them in. What's the relationship? Well, if I kind of squint, the key is to squint here. I see this general relationship here. I wouldn't describe it as anything but a straight line, right? And you don't want to be too picky here. You want to see a straight line. And so here, right, I would describe it as linear. It's negative because it's moving down, right? As x's are increasing, the y's are decreasing, right? And so it's negative. And here they've gone for moderately strong, right? Just strong is fine because we were able to see this pattern, right? That's why it's strong. Okay, good. That seems easy enough, right? You're used to doing hypothesis testing, confidence intervals, and now back to basics. Feels good, right? Like I said, end on a high note. Okay. Is this where I wanted to slip it in? Nah. So we're not ready quite to build this regression line. I'll give you the formulas, blah, blah, blah. But for now, we're just going to jump in and have this equation, right? This model, this line of best fit. And so the linear model for predicting poverty from high school graduation rates in the US is this. Now this line is very easy to get using Excel, and you'll see it in lab 10, which is the last lab. Oh, can you believe it? No labs this week, but I'll post it so that if you want to just get it out of the way, you can. And then we'll have labs in the last week, which is weird, but just how it worked out. But if you're done, then you're done. Nice. Okay. So we've got this poverty, which is our y, and we've got this little hat on here. Okay. And so this is the same as a y hat, the predicted value of y. And so y hat is the predicted value of y. So now in the regression sense, the hat means it's a predicted value, right? And we do this often where we replace the y and the x, right? This high school grad is the x with just a shorthand version of the variable name, right? Because then it's easier to read. You don't have to. You could say y hat is 64.78 minus 0.62x. That's the same, right? But sometimes I find that it's helpful to insert those little variable shorthand names. Yeah. So y hat, right, can be confusing because we've also seen p hats, right? But the context will tell you that a p hat is a sample proportion and y hat is a predicted value of y in a regression setting, right? So if you're in a regression question, then of course y hat is the predicted value. If you're doing hypothesis testing or confidence intervals about a proportion, then it's p hat. Okay. If we're told that the high school graduate rate in Georgia is 85.1%, what poverty level does the model predict for the state, right? And so here I'll highlight that it's a prediction. Okay. And what can we do when we live in a shoe? We're trying to predict poverty given some value of X. Now, you guys are really well trained and you know, okay, if it's a percentage, I have to convert it to a proportion, except in regression. Oh boy, what's our clue here? So if I have to convert this to 0.851 or just leave it as 85.1, that's going to go back to the original scatter plot here, right? You want to have your values on the same scale as what's in your scatter plot. And most of the time, if it is a percentage, we just have them as percentages and we don't convert them. Confusing, yes, but just something to keep an eye out for. So here, 85.1 is in this range, and so that's what makes more sense to use as my X value. But then remember, the output is also a percentage, right? The percentage in poverty. So here, we keep this 85.1 as our value of X, right, to match the scale on the scatter plot. Making sure you keep on top of your bed mass, right? You need to multiply these two guys before you can subtract them from the y-intercept. And then we get a predicted value of y. And so here, this is our y hat, or poverty hat, if you prefer. That's the predicted percentage in poverty in Georgia. Therefore, the predicted percentage in poverty in Georgia is 12.018%. You're better off just not rounding stuff unless there's tons of decimal places, right? Georgia is one of the 50 states, right? And so we have a data point for Georgia. And so we have an observed percentage in poverty in Georgia. And I'm kicking myself for not looking up what it actually is, right? But this is the predicted percentage in poverty in Georgia, right? We compare this prediction to the observed value of y. I'll span the two slides, I guess, or maybe put it on one. I said it all confidently and then I immediately changed it. So we compare this prediction to the observed value of y to find the residual. So it's called the residual. And remember when we said, when we just had a scatter plot and we thought about how am I going to fit a line of best fit, right? Well, you wanted to minimize those distances between the line and the points. So really what you're minimizing are the residuals, right? And so here, the line of best fit, minimizes the residuals. There's a little bit more, well, there's a ton more theory behind that, but a little bit more that we'll introduce. And so, but just broad strokes, the line of best fit minimizes those residuals. So we have this model fit, right? The least squares regression line. And so what we could do, I find it confusing, but we could think of the observed data as the fit, so the model, so from the line, and then plus the residual, right? Add a little bit of noise on each of these from the line. Or I think the easier way to think about it is the difference between the observed and the predicted value of y is the residual. This is on your formula sheet. And if you don't have one, just because we're introducing a new section, I did bring some. Come grab it or play it cool, whatever. It's at the very end. I snuck it in at the very end of your formula sheet, which is very exciting because this was a pretty overwhelming formula sheet. And we've kind of picked away at it. And here we are. You've made it. Yes? Yes. Grab one. No worries. Did I grab this? Yes. So on the formula sheet, I have it like this. The observed value of y minus the predicted value of y. I really should have it like this. The residual is yi minus yi hat. Somewhat confusingly, but we'll see why in a second. The residuals are denoted by e, so lowercase e for error. Or residual. So each point has an error or a residual, and that's why we have the subscripts. Okay. And so if we talk about DC, where's DC here? We have this observed value of y, but at that same value of x, right? I can use the model that we built, or we were given rather, to predict the value of y, right? And so here, if I trace this over, this is my y hat versus kind of, that's pretty good, minus my y, right? So my residual, oh, sorry, my residual is the y minus y hat. That means that if the point is above the line, I get a positive residual. And if the point is below the line, I get a negative residual, right? Just how subtraction works. Okay? And so we don't know what these values are, but we could guesstimate or use the data and we can calculate that DC is 5.44 percentage points different from the model. Oops. Eek. Yeah. So one of the terms that we're going to introduce that you're probably familiar with just from life is the correlation. Okay? We use it in kind of a sloppy way when we use it in speech, right? Oh, there's a correlation between these two things. And so, but for us, right, the correlation describes the strength of a linear association or relationship between two variables. In fact, it also describes the direction. Okay. So I'm going to add that in here. The correlation is a numerical measure of the strength and direction of a linear relationship. So it has to be linear. Is a numerical measure of the strength and direction of a linear relationship. Okay. It has to be linear. This feels similar to if we had a normal distribution, then I knew that, okay, the numerical measure of the center is the mean, and the numerical measure of spread is going to be the standard deviation, right? We had a scatter plot, and we said, okay, I have to describe this thing. Is it linear? Is it nonlinear? Right? What's the strength? What's the direction? And so now the correlation is that numerical measure of the strength and the direction of a linear relationship. So it has to be linear in order for it to apply. The problem is we can always calculate the correlation. Okay, just like we can always calculate the mean, but it doesn't always apply, right? That's our job to know whether it applies or not. And so let's see here. Maybe I'll throw it up here. We can always calculate the correlation, but it only applies to linear relationships. But it only applies to linear relationships. Very similar to the mean and the standard deviation. We can always calculate those things, but they only really apply if you have a normal distribution. So the correlation takes on values between -1, which is a perfectly negative relationship, and +1, which is a perfect positive relationship. And then in the middle, if we have a correlation of 0, then there's no linear association or there's no relationship between these two. So what I usually do is I make this kind of number line. I don't need the plus on there. Got caught in the loop with 0 in the middle. Okay. Let's talk about what does a perfectly negative linear relationship look like? Well, we said it looks like if I have my line here, a perfect relationship means that every point is exactly on that line. That's not going to be the case, right? You're going to have maybe something that looks like this. Still linear, right? Still strong, right? So here, if the correlation is somewhere here, then it might look like this, right? So it's going to kind of soften up around the line, so to speak, as you move closer to 0. If you have a correlation of 0, then you have this cloud, no relationship there. And then if you move out towards a positive relationship, right, you might have kind of, or maybe I should bump these over here. Might have something like this, right? A relationship there, but it's not perfectly positive, but it's generally, right, moving in the upwards direction versus here, a perfect positive relationship. Those are never going to happen, mostly because they're not interesting for modeling reasons, right? A lot of kind of manufacturing data is perfectly linear, right? You put in some amount of man hours and you get out some predictable, right? Very predictable amount of product, right? And so that's boring. We don't tend to model that, right? It's good to know the relationship, right? But we don't tend to model that. We tend to focus on these guys, a little bit of action in there. Okay. So, and maybe I'll draw an arrow maybe here. As a guide, okay, So of course, if the correlation itself is negative, then you have a negative relationship. I didn't say that, but I think we were all hopefully kind of on board with that, right? Generally negative. And then if the correlation itself is positive, then you have a positive relationship. And so that's how it describes the direction, right? And so let's put those on here. So here we have a negative relationship, and here we have a positive relationship. Color haven't I used? Oh boy, I'll use pink again. I use as a rough guide a correlation of 0.5 on either end as kind of my transition from a weak to a strong relationship. Okay, some fields, like I think, is it psychology? They have like 14 different breakpoints. Oh, if it's between this and this, then it's moderately strong. You can't say it's moderately strong, it's between this and this. Anyways, I just have the basically one breakpoint, right, at 0.5. Now, negative 0.5 and 0.5. So in this region, I would call it weak. And of course, out here, I have a strong positive relationship. And here I have a strong negative relationship. This is just as a guide, right? The 0.5, negative 0.5, 0.5. There's some wiggle room there. That's why I used round brackets. It's up to you, right? But if you are given a correlation, right? So if I tell you the correlation is 0.6, right? Then you know that it's a strong positive linear relationship. Okay, so just to kind of get into the correlation, here's our relationship that we have, and we want to guess what the correlation might be. Okay, so we already decided that we have a negative relationship. We have some facts up our sleeves, right? The correlation has to be between -1 and 1. And so we can eliminate a lot of these options right away. The most glaring one is the -1.5 is not any correlation ever. And so that one's out. We said we have a negative relationship, which means that the correlation has to be negative. And so both of these positive correlations are out. And then I'm choosing between -0.1, which is very small, right? Very close to 0, and -0.75. Even if, you know, in your gut, 0.75 feels high, right? Just looking at this relationship, it's the most likely correlation, okay? Because a -0.1, we already said, well, I can see a pattern, right? And so here, because I see a pattern, it has to be the -0.75. What about, oh, whatever, this one? I'll let you try it while I drink some water. It's a new X variable, same Y variable. Wait. This one's harder. Should have let you do the previous one first. On your own. Why is it harder? Looks like a weaker relationship, right? We're talking about the relationship between the percentage in poverty and the percentage of female householder, no husband present. Kind of a weird variable, but whatever. If I had to, that's kind of what I'm seeing as a pattern. Oh man, I think I've got these huge things, but also annoying. I gave you a clue by drawing those lines. Has to be positive, right? So immediately those negative values are out. There's no gimme ones here. They're all between -1 and 1. Okay. We had a hard time seeing the pattern, so it can't be 0.9, right? And so that one's out. Or I had a hard time seeing a pattern. I don't know, telling you what you saw. So for me, I'm choosing between 0.1 and 0.5. I could be convinced of either one, right? Especially in this kind of guessing game. I'm gonna go with 0.5 just because once we drew these lines, then it was like, oh, I see it now. Okay, sure. Right. And so I could be convinced of the 0.1, but because we were able to see this pattern and generalize this pattern, and again, I do chop some off, right? It's just a sample. And so it's just broad strokes. And so I'm gonna go for the 0.5 because I was able to see some sort of pattern, but it is weak, right? And that's what 0.5 looks like. Okay. And this does have a correlation of 0.5. And that's why I use 0.5 as kind of a cutoff, right? It's hard to see stuff. Okay. Of these four relationships, which one has the strongest correlation? Now, of course, A is a decoy. Why? Because it's not linear, right? And so the idea is this: if I fit a straight line here, the correlation is going to be very, very small because the correlation tells you how close all the points are to the line. Now, except for here and here, where the points are very close to that line, everywhere else, they're really far from that line. So that's the danger, is that you might be calculating a correlation for a nonlinear relationship. It'll do it, but it'll be low, right? Whereas here, we have this linear relationship, and compared to the rest of the graphs, those points are the closest to the line, and so it'll have the highest correlation. I will say here, A has the strongest relationship, but because it's non-linear, right, then the correlation doesn't apply. A has the strongest relationship. That's true. That's still true. But the correlation does not apply since it is not linear. In fact, the correlation would be low. The correlation would be low. Okay. I'm gonna add a page here. Oops. On your formula sheet, there's a huge ignorable section, or somewhat ignorable. So this is where we finished the day before the test, right? We built up to comparing two sample means, right? Feels good to have that done. And now we're talking about the correlation, and I'll introduce the covariance here. Wow, SXY is called the covariance. S subscript X subscript Y is the covariance. I only mention that because it might come up in an assignment where it says the covariance is this, okay? I'll never get you to calculate these. And so you can kind of, what's an ignore color? You can kind of ignore all these formulas. It's two different calculations that you could do to find the covariance, but I'll just give it to you if you need it. When would you need it? You would need it when we calculate the correlation, which is denoted by R, which I think I haven't said yet. Bad, Emily, bad. We are not going to use this crazy formula to calculate the correlation. In fact, Excel just calculates the correlation easily for us, given some X and a Y variable in your spreadsheet, right? That's all it needs. So here, R is the correlation between, maybe I'll do that. Between X and Y. I will say that I use a lowercase r just because that's the most common thing that we use, and old habits are hard to shake. And so here, I use the lowercase r, and capital R is in the textbook. It's funny because it's quite clever that they use capital R in the textbook. I just can't bring myself to do it. I don't know why. Just too ingrained. Okay, but they're used interchangeably. So if you see a capital R, it's fine. It's just the correlation. You're expecting the correlation to be between -1 and 1, right? And so if you have the covariance, SXY, you have the standard deviation of your X variable, the standard deviation of your Y variable, right? Then you can calculate the correlation if you had to. Okay? Most of the time I just give it to you, but if you had to, then this is the way that we would calculate it. So you can also ignore, right, the rest of those. Well, that simplifies that formula sheet a little bit, right? And so ignore these. Whee. They're on there, but we're not going to use them. Okay. Now I think we're ready. Ready for what? The next section, 8.2. Earlier, we just said, here's the line, here's the model that we're going to use it to predict a value. Great, cool. Now we're going to talk about, well, how do we get that line? Yeah. So we've already established that we want a line that has small residuals, right? In fact, we want to minimize the residuals. But if we're trying to minimize a value, and some of them are negative and some of them are positive, if I add those all up, then I end up at 0. That's just how the line works. And so what we need to do is we need to make them all positive somehow. And we've seen that before when we calculated the standard deviation, for example. So we've got a couple of options, but really we just always use option 2. It's nice to see that, they tried some stuff, didn't work, it's too hard. And so we just use option 2. But the first option would be, okay, what if you just take the absolute value, right? Add those up, and whichever line gives you the smallest sum, right? Minimizes the sum of those absolute values. That's the line that you pick, right? What are you doing in theory? You're fitting all the lines possible and then picking the one that has the smallest sum. We don't do that, software does that. But in theory, and there's a lot of background stuff happening, but that's what it's doing. And so another way to make negative values positive so we can add them up is by squaring them, right? If I square a negative value, I get a positive. And so what we do is we fit a least squares regression line. So the error term or the residual squared for each data point, and then I add those all up and I find the minimum value. Right? And so why do we use this one? It's the most commonly used, that's say no more, right? It's easier to compute by hand, but also for software, it's faster, right? If you've got a huge data set, then that is a concern. And so, but one of the key things is that most of the time, if you have a residual that's twice as large as another residual, right, meaning it's further from the line than the others, right, twice as far from the line as the others, it's usually kind of twice as bad or more than twice as bad, right? So you don't want to have a one-to-one relationship. So just to illustrate. If I have a residual of 1 versus a residual of 2, residual of 2 is twice as large as a residual of 1. 1 squared is 1, but 2 squared is 4. So now it's reflecting that, okay, it's not just twice as bad, it's actually 3 times as bad. Right? And so that's why we use the squares. You don't have to remember that, but it is kind of a fun thing. Okay. Oh boy, now we're back to inference, sort of. We have a sample, right, of information, and we're trying to use that sample to build a model, right? And so we're going to have point estimates for our model, but really what we're trying to do is we're trying to learn about the whole population, right? And so what we have is we have this model here for the population, right? And so y hat is beta naught. Now beta is a Greek letter with it's a fancy B with a little tail on it. Beta naught is the population y-intercept. I'll say this is the population model. We don't have the population model. We're trying to learn how this population behaves. Maybe I should come up with a beta fish example to try to find the betas. Kind of confusing, I guess. Anyways, I'll try. I'll probably forget, just like a beta fish, as soon as I leave this room. So beta naught is how we're going to denote the y-intercept, right? Which we just call the intercept because it's the only one we care about. Beta 1 is the slope, and x is still the explanatory variable. Okay? This, just convince yourself that this looks the same as y hat equals mx plus b. Little switcheroo in the order, but whatever's attached to the x is the slope, right? Change in the variable names, but generally same type of layout, right? So what we're going to have is we're going to have the population intercept, beta naught, and we're going to have some point estimate. Now that's the thing that we're going to be working with, and we're going to call it b naught. Oops. So far, y hat is b naught. plus the slope. Well, we're trying to learn about beta 1, but we don't have it. So we take our sample information, our point estimate for beta 1, and call it B1. Why not? Times X. So this is the model that we'll be building, right? And I'll just grab it from the formula sheet. Did you think that we would talk about the entire formula sheet today? Or I guess finish talking about the entire formula sheet today. It's crazy. I'm going to bring it in again, but just so you can see. I really kind of talk you through it. If you let the formula sheet talk into what all the things are, they are on there, right? And so the least squares regression line is y hat is b0 plus b1x. And then I tell you that the slope is b1. Okay. In fact, I even tell you how to calculate the slope. That's not that crazy. It's the correlation times the standard deviation of your y's over the standard deviation of your x's. Now, this is where it's super important that you keep track of which one is your y and which one is your x. Think about 2 divided by 1 versus 1 divided by 2. Right? So it's going to make a big difference potentially. Okay. And so you want to keep track of which one is your x and which one is your y. Of course, I give you this information, right? The standard deviation of each variable, the correlation, and then you can calculate the slope, right? And so here it tells you that B1 is the slope, right? Why do I have to find the slope first, even though it appears second in the equation? Well, it's because I need it to find the intercept. Kind of a fun fact. The line, so the least squares regression line always passes through x bar, y bar. It's kind of just a fun fact, not worth remembering or anything, but that's what we're using to find this y-intercept. Okay, y bar is the average of the responses, x bar is the average of the explanatory variable. Again, things that I would have to give you, right? And then it's just a matter of plug and chug. Math's not crazy, right? And so it's all on here telling you that the y-intercept is B0, right? And so we're feeling good. This point estimate parameter business, though, should make you feel like, uh-oh, are we going to do a hypothesis test? We could. We might, if we have time. I doubt it. It's not on the final exam, so I tend to not really talk about it, but we could, right? We usually don't care to hypothesize about the y-intercept. It's not really, it's just an anchor for our line. And so usually we don't care about that. But if I have a point estimate, and in the output, we would be given the standard error. So we're not even going to talk about that, but it has some spread, right? Because it is from a sample. And so same as before. But if we think about the slope, if a slope is 0, right, then let's just draw it here. Slope of 0 looks like this. That looks like no relationship between these two things. Right? I could plug in, like I said, a low value of x and get the same value of y as if I put in a high value of x. I would get the same predicted value of y regardless, right? So that's useless information. That's a useless relationship for me to model. So what could I do? I could talk about, well, is the point estimate for the slope significantly different from 0, right? We know how to do that. If I have a point estimate, I have some null value 0, right? How far is B1 from 0? I'm given the standard error of B1, right? And then I get a t. We know how t's behave, right? We can find the p-values and see if if it's significantly different from 0. That's really fun, right? You can kind of see how there's lots of different inference that you could do, and you now have the tools to do it. I mean, a parking lot that, but we'll just keep it in mind. A couple of conditions that we need to check. Most of them are obvious. Well, the first one is obvious, at least. In order to model it with a straight line, it has to be linear, right? And so we can't use a straight line to model something that's not a straight line. That's pretty straightforward, I think. Now they have these conditions kind of outlined further in the next few slides, but I just want to do them here. So we have to have, in order to model with a straight line, the relationship must be linear. That's obvious, I think, at this point. The next condition for having this model and having it fit our data is that we need to have nearly normal residuals. So what we said before was, okay, each data point, right, each state in the US and DC, we can calculate a residual, right? And so now I have a sample of residuals. That's numerical data. I can make a histogram, right? And so here, we can generate a sample of residuals. And so what we can do is make a histogram of the residuals and make sure they're approximately normal. In fact, they should also be centered on 0. Right? What's a residual of 0? Means that the point is on the line. Most of them should be around the line, close to 0, and then a little bit of spread. We can make a histogram of the residuals. And it should be approximately normal, centered on 0. The constant variability is also called homoscedasticity. Can I spell that? Homosceda, or I feel like it's a K maybe. I'll make it look kind of like both. Skedasticity. I feel like it's okay. It's in a slide further down. I mentioned the term, even though it's hard to say and hard to spell, but because if an assignment question, that this isn't going to come up on the final exam or anything, but if an assignment question mentions it, then it's good to know that it's actually just constant variability. Now, what does that look like? Around the line, you've got relatively constant scatter around the line. So here, this is constant variability. Versus if I have something that looks like this, non-constant variability. The problem with using this line is the fact that I have very precise predictions down here for this range of X, right, is muddled by the fact that I have kind of very imprecise predictions for this range of X. That's a problem, right? Because then you would want to break it up. Okay, I've got this awesome model down here for this range of X's, and then it really clunks out for the rest of the X's, right? And so that's why we need to make sure that we have this relatively constant variability around the line. And we can check these using residual plots. How do I know what time it is? Make the most of them. We can check these conditions using what we call residual plots. Now, residual plots are going to be these little guys down here at the bottom. So here we have the original plots, oops, with your response variable on the y-axis and your explanatory variable on the x-axis. It's the same for all three of these. Now, the residual plot is still going to have the explanatory variable on the x-axis, but remember, in your data set, you've got your x's, your y's, and you're also able to make a column of the residuals, right? And so you can link your residuals to your x's and your y's. And so here, your residuals for a residual plot go on the y-axis, and it's centered on 0. It's hard to convince people that you need a residual plot, because does this look basically the same as this, just laid out at 0? Yes, it does, right? But what do we notice here? Of course, it looks the same, but it amplifies or it magnifies that non-linear relationship. So it's a little bit easier to see here, whereas here, especially without the line, it might be hard to pick up on that. And then this is supposed to be an example of non-constant variance, but I would let it slide, I guess. But the residual plots, we use residual plots to magnify the original scatter plot, right? And to find those conditions violations. We use residual plots to magnify I'll say the relationship in the original scatter plot. So we can look at the original scatter plot, and we've got Rhode Island here had a negative 4.16 residual. And so here, Rhode Island, and if I drop it down, right, then the residual is negative 4.16. And we're looking for random scatter around 0. Did I write that down? No. We're looking for random scatter around 0 in the residual plot. So we can make these residual plots, or I might give them to you. And I'm going to skip through here. It's just getting you to check the conditions. And for Thursday, find the least squares regression equation given, I don't know why I capitalized that. Given the mean and the standard deviation of your X's and your Y's, and maybe pretend that the X and the Y aren't given to you, just so you can have some practice kind of gathering this information that you need and the correlation. And then we'll use that as review on Thursday, where we'll pick up, keep going. If you have any questions, let me know. Otherwise, I'll see you then. Stop this recording.